All right, so the second agent of metamorphism is going to be confining pressure and differential stress, so overall pressure. So pressure, like temperature, increases with depth because the thickness of the overlying rocks increases. Buried rocks are subject to something called confining pressure, which is analogous to water pressure, in which the forces are applied equally in all directions. So in confining pressure, it will cause the spaces between mineral grains to close because there is pressure in all of the directions and it's equal in all of the directions. This produces more compact rocks that have greater densities overall. If the pressures are even greater, the atoms that make up a mineral are sometimes caused to pack more closely together to produce a new and denser mineral for the most parts, which ends up being a phase change, is what it's called. Sometimes rocks are subject to directed pressure, in which case the forces deforming the rock are different in the different directions, and these type of forces are referred to as differential stress. Differential stress is greater in one direction than in the others. There are different types of differential stress, of which we will only discuss one, namely compressional stress. So this compressional stress happens when there is differential stress that is squeezing a rock mass as if it were placed on a vise. So it's squeezing it in two or in opposite directions, but only in one cardinal direction, if you would. So rocks exposed to compressional stress are usually shortened in the direction of the greater stress and are usually elongated or lengthened in the direction that is perpendicular to stress, or the directions that are perpendicular to stress. In convergent plate boundaries, for example, the greatest differential stress is directed horizontally in the direction of plate motion. Consequently to this, in these types of settings, the crust is greatly shortened horizontally, which means that it's going to be thickened vertically, which results in mountainous topography like we see in the Himalayas, for example. And this is the scenario that they're showing right there. So in high temperatures and high pressure environments, rocks are ductile, which allows their mineral grains to flatten, as we're seeing in the image to the right. For example, this is sort of the way that it occurs. This squeezing mechanism happens at various scales, not just at the macro scale, which causes the mountainous regions to deform, but we also see a lineation of certain grains, making them more elongated in a perpendicular direction to the stress direction. So a scenario more like this one, where in this granite, all of the minerals are sort of free to roam wherever they want. And then after that compressional stress is applied, then you get the minerals elongated in the direction perpendicular to the greatest stress. So this elongated minerals end up lining up to make foliated textures. And we will see this in the next few slides. But foliated textures are these type of textures where the minerals are oriented in one specific direction. So, as I said in the last slide, in high temperature and high pressure environments, rocks are ductile, which means they're plastic-like, which allows their mineral grains to flatten. But on a larger scale, rocks that are ductile deform by flowing rather than breaking or fracturing when they're exposed to this stress. This process forms folds, as the one that you're seeing in the image on the slide. By contrast, in near-surface environments where the temperatures and pressures are relatively low if compared to these metamorphic rocks, rocks tend to be brittle or more rigid. So when exposed to stress, they tend to fracture in these scenarios. So again, at high temperatures and high pressures under stress, these rocks metamorphic rocks tend to be ductile, meaning flow more, and form folds, so bend. in near-surface environments under low temperatures, low pressures, rocks tend to be more brittle, meaning more rigid, and they tend to fracture rather than fold. So water is abundant in Earth's crust. In the upper crust, water occurs as groundwater. At depth, hot water is released into the surrounding rocks when a magma body cools and solidifies, for example. In addition, many minerals such as amphiboles, micas, and clays are hydrated, which means that they contain some water in their crystalline structure. Elevated temperatures and pressures, which are typical in metamorphism, causes these types of minerals to dehydrate, which means to expel the inner water outside, and the mineral becomes waterless, if you would. So the hot chemically active fluids that are driven out of minerals or out of the formations enhance the metamorphism by dissolving and transporting the ions from one site in the crystal structure to another site, which will facilitate the recrystallization process. So the fluids become more reactive the hotter they are. Okay, so the cooler they are, the less reactive they are, meaning the less amount of recrystallization that they promote. The hotter they are, the more recrystallization that they will promote. So the transporting of those ions within the crystal. This fluid action is common to occur near magma bodies. So in some cases, if the rocks near a pluton differ greatly from the pluton itself, where the water is expelled from, then there is an ionic exchange between the fluids and the surrounding rocks. And this process is called metasomatism. So this occurs, for example, in the formation of the mineral wollastonite, which is a mineral that forms by the ion exchange of silica-rich fluids and calcite, which is a primary ingredient in limestone. So imagine this occurring the following way. You have a nearby magma body to a limestone that has been buried deep within the earth, and it's near that magma body, right? The magma body is heating up fluids nearby, and those fluids may be just simple water that was within the pores of a nearby rock. So those hot fluids now will travel and they will be silica rich, as that rock where they came from was full of, let's say, silica, and so they will travel towards or inside the ground and exchange the ions of silica with the limestone calcite ions, if you would. And so they will deform the calcite and transform it into the mineral wollastonite. So I know I made a few weird kind of switchbacks in that explanation, but I hope that it was still useful to understand that process of metasomatism. So most metamorphic rocks have the same overall chemical composition as the parent rocks from which they formed, except for the loss or the acquisition of volatiles that they have, for example, or from the ions from that hot circulating fluids that might change the ionic composition. But overall, for the most part, the metamorphic rocks will retain the characteristics from the parent rock. So, when we try to establish from what parent material a metamorphic rock is derived, the most important clue comes from their overall chemical composition. Typically, the parent rock and the new metamorphosed rock will have the same color scheme, for example. And I think it's sometimes easy to picture this if you consider both rocks, the parent rock and the new rock, to be blended and see if that blended material looks similar in a color scheme. So that helps. Second, the mineral makeup of a parent rock also largely determines the degree to which each metamorphic agent will have caused change. So, for example, when magma forces its way into an existing body of rock, the high temperatures and the hot fluids may alter the host rock. If this host rock is composed of minerals that are comparatively non-reactive, such as quartz, any alterations that may occur will be defined to this narrow zone next to the igneous intrusion. So I try to show you this through this image right here. But if the host rock, for example, is made up of calcite, and calcite is highly reactive, then the zone of metamorphism may extend far from the intrusion. And I try to show you that over here. So the image doesn't do a very good job at it, but it kind of shows what I wanted enough. So in this case, this is the igneous intrusion. So overall it is hot and it's causing, before it crystallizes, it is hot and it's causing some sort of metamorphism with the host rocks. And there are many different types of host rocks. So we're seeing that when the igneous intrusion is in contact with the sandstone, most of the minerals in there are quartz, obviously. And so the zone of metamorphism, which is the zone close to that magma body, will be a little bit thinner than the zone of metamorphism over here, where the intrusion is in contact with limestone, which is made up mostly of calcite, which is highly reactive. So this zone of metamorphism, although it's not shown as great in the image, should extend quite a bit further for the limestone host rock than for the quartz sandstone host rock. So metamorphism will occur close to the intrusion for rocks that have non-reactive minerals, and it should occur a little bit further from the intrusion in host rocks that have more reactive minerals.